every node will have a sensor, and the sensor node, if it is consuming large power, then your battery will be down quickly. So because imagine in a wireless network, you have more than 100 nodes, and each node is remotely put, and each node is power supplied by a battery. So if the battery power goes down, what will happen? The circuit will not work. So your electronic circuit that you are engaging in the particular node should consume very less battery power. So the battery life must be extended. Otherwise, every now and then you may have to change the battery. That will really make the efficiency poor. So what we need is, we need digital output, and such a digital output producing circuit or producing sensor should consume least power. That is the requirement of the present day situation. The present day, you cannot have a huge electronic circuit which consumes, say, 100 milliwatt or 200 milliwatt power. If it consumes that much of power, then the battery life, so battery technology also is changing, but you need efficient energy consuming system. So the power management is very, very important. So if the power drawn from the battery is too high, your node will fail frequently. So ultimately, your process, because nowadays, imagine we are trying to control every process through a remote area. Everything is connected in a network like IoT, and you can control a big plant using a wireless sensor technology. But the very important point here is, wireless, the sensor that is used for a wireless node should consume least power. That is a very, very critical point. So, for example, I am just telling you a tire pressure monitoring system. Now you see, in every car there are 4 tires, and now every tire will have a pressure sensor which will measure the tire pressure, and the tire pressure must be conveyed to the dashboard. Now what happens is, you cannot connect the sensor output through a wire because the wheel will be rotating. So the wireless sensor should be put in the wheel. Now the pressure sensor that you put in the wheel should have digital output, and the generation of the digital output should be established or should be achieved with least battery energy. Then only I will be having long life for the battery, so the communication equipment will work fast. For example, nowadays, if you, in the recent days, cars, if you see, your remote battery, if it is very weak, then the dashboard will tell. So you will know the remote is going to fail soon because the remote battery is going down. So the battery life will be extended, and if you have to frequently change the battery, that is not economical. So if you have to use, if you want to gain, if you want to have best power management system, the sensors that you use and the wireless network that you use should consume less battery power. So we have different techniques for making the wireless node energy efficient, but the sensor, if it is consuming high power, then all purpose will be lost. So what the need is, we need a tire pressure sensor, and that should have a simple signal conditioning which will give a digital output. So that is what is the need. So I have summarized here the commercial pressure sensor, problems with the commercial pressure sensor with the digital output. So they have high power budget, highly undesirable for wireless sensor nodes or IoT applications. They use complicated electronics, so that will make the cost of the fabrication very high, because when you want to when your electronics is complicated, the die size will be more. So in a wafer, if the die size is small, you will be able to get more number of chips. Now, if the die size is more, number of chips per wafer will be reduced. So the cost of the fabrication will be very high. So complicated electronics should be avoided. And thermal budget. Now the technique that you use, the pressure sensor, especially when you measure pressure, you should not have any temperature. The pressure should not be affected. Pressure measurement should not be affected by temperature. If that has to be in piezoresistive sensor, if you see the temperature changes, piezoresistor resistance also will change. Then to compensate for that, you have to have temperature compensation circuit. So that will add cost. So now finally, the MEMS and electronics must be co-fabricated in a single chip. So our idea was, to avoid these problems, you should have a pressure sensor that will give you pressure, as well as it will give you pressure in the form of digital information. So once I have digital information, transmitting that will be very simple with the current day technologies. Okay, so the co-fabrication, there are two different approaches. One is MEMS first and then CMOS second, or CMOS first then MEMS second. But both MEMS as well as electronics is being put together in a single chip. So now what is the solution? So we need to identify a structure which will measure pressure, and the same structure will be able to give you a digital signal also. So we need a simple structure with preferably all MEMS components, no electronics, no electronic components, no electronic circuits. The MEMS structure itself converts the pressure into a digital signal. So that is the first thing. Second important point is low power design. So such a structure should not consume large power. So if it is used in a wireless sensor node, the sensor should not consume large power. So low power design is critical. So digital readout from the sensor with simple signal conditioning or processing electronics. So no A to D converter should be there. If you use a to D converter, then that complexity will be more. So finally, we need a highly linear device with high sensitivity, because linearity is very, very important, because throughout the span, you should give very good linearity. Then only I would say the sensor is useful, or it is doing some good job. And whatever technology that I develop, it should be CMOS compatible. So these are the requirements for a pressure sensor for wireless communication networks. So I have explained you the background. Now, a PWM, pulse width modulated pressure sensor, we have evolved, and let me explain you the evolution of PWM pressure sensor. So this pressure sensor will be able to give a digital output with the least power. So that almost zero power will be consumed by the sensor. Still, it will be providing a digital output. So that is what we are going to see next. Now I will let me stop for a single minute. Let me have your feedback. You can unmute. One or two people can unmute and tell me whether you understood what I am trying to say. Anybody? Am I audible?
Sir. Yes, sir.
Yeah. So one of you can just tell me if 2 or 3 sentences what I have tried to communicate. I think there are a lot of teachers. You can unmute and talk to me.
Dear participants, you can interact, sir.
Two, 3 sentences sufficient. Or let me ask a question. What is the major problem with the present day pressure sensors which are already available in the form of integrated circuit and which can give digital output also? Something like this. So what is
complicated? They have complicated electronics, sir.
May I know what is your name?
Good morning, sir. I'm Salakshi, sir.
Complicated.
They have some complicated electronics involved in it.
Okay. So that will result in what? When the electronics
result in more power consumption.
Very good. More power consumption. Any other issue? More circuits, more electronic components. Then what will happen? More real estate. It will occupy more area. Yes or no?
Yes, sir.
So when it occupies more area, the size of the chips become more. But what we need nowadays, the trend is miniaturization. So the area is more means what will happen? In a square inch, if I get 10 integrated circuit, I can sell it for a cost. And in a square inch, if I get 1,000 chips, the cost will be reduced. Yes or no? Follow my point or not?
Yes,
so
yes,
when the circuit becomes complicated and large, the area of the integrated circuit will be more. So the size, when the size becomes more, in a single wafer, the number of integrated circuits that I will be getting will be less. So that will increase the cost. Nowadays, it is a very competitive world. If X is giving a sensor for 100 rupees and Y is giving for 15 rupees, people will go to the person who is giving for 15 rupees. So that is how the China products are selling more. Follow my point or not? So there is cutthroat competition. So if the area is more, you need more money. I mean, more fabrication cost. Yes or no? So that is the thing. So what ultimately we need is a pressure sensor which will use all MEMS components, all mechanical components. Now, mechanical components and least electronics, the least electronics. Still, you get a digital output. So that will give you what? Plenty of, that will give you a great advantage. So that was the concept behind this PWM pressure sensor. Okay. So now let me just give a simple idea about a PWM concept. So the signal from the sensor, let us call it as message signal. So let us say it is V of S, and the carrier signal is a ramp signal. So when you compare it with an analog comparator, we know analog comparator. So when the carrier signal voltage is less than the message signal, your output will be low. And when the carrier signal is more than the carrier signal, the output will be high. So if the message signal is small, the pulse width will be less. If the message signal is more, the pulse width will be large. So the magnitude of the message signal that is converted into a corresponding pulse width. So that is called what? PWM concept. So now you can say it is almost a digital signal, because the pulse width I can easily count using a counter. So what you need for a PWM pressure sensor is what? You need a ramp generator. Hello? You have any doubt? I heard somebody talking something. Okay. So now here you see a PWM pressure sensor can be constructed using a conventional pressure sensor also. But in that case, you need a piezoresistive or capacitive pressure sensor and a signal conditioning electronics, a ramp generator. So we can generate an output. But again, the problem will not be solved, like the least power. That will not be achieved. So to achieve that, what we are going to do is, we are going to combine a MEMS pressure diaphragm and a switch. So let me explain you through a simple concept. Suppose imagine you want to measure the level of a liquid in a beaker. So now you see, if you consider the base as the level, the first diagram you see, the base as the level. So delta is the level of the water or the liquid. So from the reference diaphragm, how much deflection you get? If you are able, now you see the reference diaphragm is the diaphragm that is clamped in all the four sides, and I am measuring the delta, the deflection of the diaphragm. So that is used in conventional pressure sensor. But there is another way. The diaphragm is here. Now there are two fixed diaphragms. There are two levels, fixed levels. Now, when I am applying a pressure, there is a deflection. So now the D naught, that is the distance between the deflected part and the top reference structure. So that will give an idea. So now you can measure D naught. That also will give you what? Pressure. So now in the PWM pressure sensor, what we are going to do is, we are trying to have two references. One is a deflecting diaphragm, the other one is another level. So now what I will do is, the pressure will naturally cause a deflection to the diaphragm. So I will now measure the remaining air gap. Suppose imagine if the pressure is the maximum and if the diaphragm is touching the top plate, then it is what? The maximum pressure. So air gap is 0. So the first one is like piezoresistive component concept. The second one is like capacitive concept. But now I am not going to measure capacitance here, but I am going to use a different technique to convert this into a digital signal. Okay. So now what I am going to use is a RF switch employed PWM MEMS pressure sensor. So what I am going to do is, a RF switch, it is basically a cantilever beam with a fixed, with one end fixed. And if you apply a voltage to RF switch, it will, due to the electrostatic force, it will move downward or upward. Okay. So now, suppose imagine the air gap is D naught. Air gap is D naught. For every air gap, what will happen? There is a voltage that is called pull-in voltage. So at the pull-in voltage, the electrostatic force will be required enough to put the switch down on the substrate. So that way, a switch will be closed. So I have a suspended switch. The suspended switch, I am applying a voltage. When the applied voltage is more and more electrostatic force will be there. So the cantilever beam will be pulled down, and at a particular point, it will collapse and it will fall on the substrate. So that is the basic concept of RF switch. So it is basically a mechanical switch. So now, what I am going to do is, you see the deflection of delta. Delta is the deflection of the diaphragm. So that is directly proportional to pressure. So delta is equal to C2P. C2P. C2 is a constant. A is the diaphragm size, H is the thickness of the diaphragm, E is the Young's modulus. So C2 is a constant. So the deflection is directly proportional to pressure. Okay. Now you see the pull-in voltage equation. It is 8 times K. K is the spring constant of the switch, and D naught minus C2P. C2P is what? Delta is C2P. So the pull-in voltage is basically becoming a function of the pressure. So if the pressure is more, the deflection will be more. Now the pull-in voltage will be less. Okay. So that is what you need to understand. So when the pressure is more, the diaphragm will move up, will be a curved plate like this. Now the switch will be very close to the curved plate. So the switch will close with lower voltage, So when the voltage is, when the pull-in occurs, the switch will be closed and I will get an output signal across a resistor, across the resistor. Let one of you tell me whether you are trying to understand this point. Anybody? Just tell whether you are trying to understand. This is a key point that you have to understand.
Sir, can you repeat it once again, sir?
You want me to tell again?
Yes, sir.
Okay.
Thank you, sir.
Okay. See, first of all, you should know what is a switch, RF switch. Now, RF switch is basically a cantilever beam. You see the diaphragm. Diaphragm is down. The top one is RF switch. That is basically a cantilever beam. Now, when I apply a voltage over the RF switch, now the RF switch will move down because of the electrostatic force. So when the deflection is, now you understand, the RF switch will bend downward, downward. Do you see my video, my face? I think you will not be able to see. Okay.
Yes, sir. Yes, sir.
Okay. So now you see, this is the switch. When I apply a voltage here, the voltage, when I apply a voltage here, due to the electrostatic force, the RF switch will bend downward. Yes or no? So at a particular point, the switch will be closed. Switch will fall on the substrate. So I can say that it is a short circuit. So that is how an RF switch works. Now what I am going to do is, now I have applied a supply voltage VCC to the switch, and I have the other end of the switch I have connected to the resistor. So when the switch is closed, the supply voltage will come across R. Now where I will connect to the supply voltage and where I will take the voltage across, so that you need to understand. So here I have a diaphragm where I will apply the pressure. So when I apply the pressure will deflect the beam upward. Now the pull-in voltage. What is pull-in voltage? The minimum voltage that is required to make the beam collapse, to make the RF switch collapse. Collapse means what? It falls on the substrate. It falls on the substrate. You understand my point? So when I apply that particular pull-in voltage, the RF switch will fall on the substrate. So now the pull-in voltage depends on the air gap. The air gap between the fixed substrate and the moving substrate. So if the air gap is more, I need large voltage to make the beam collapse. If the air gap is less, I need less voltage for the beam to collapse. Okay. So now the RF switch pull-in voltage is given by this formula, square root of 8K D naught minus C2P. Actually it is delta. So delta is the deflection. So C2P is equal to the deflection. So the pull-in voltage is directly proportional to the pressure. So if the pressure is more, the pull-in voltage will be what? Less. Okay. So that you understand. If the pressure is more, pull-in voltage will be less. It is inversely proportional, because when the diaphragm deflects, the air gap will decrease. So when the air gap is less, the pull-in voltage will be less. So the switch will close earlier. So, the next slide, when I explain, you will understand this better. So, don't worry if you have some doubt. You see here. Now, you keenly watch this diagram. Watch this diagram. Do you see a cantilever beam in the top? That is RF switch, a blue color one, a cantilever beam. So the bottom is the pressure port. The square line I have drawn with an arrow, that is, there is a cavity inside. So through that, the pressure will be applied. Okay. So now I am applying the ramp voltage to the cantilever beam. It is called lateral actuation. I am actuating it. So the beam will move up and down depending on the what? Ramp voltage magnitude. So depending on the air gap, the pull-in voltage will change. So if you see here, the next slide I will show you. The cross section I have shown. Now you see, when I apply the pressure, the air gap will change. When the air gap changes, the top actuation electrode I have applied the ramp signal, So the ramp signal will be applied on the diaphragm, on the cantilever beam. So when the diaphragm, now what is the air gap at normal zero pressure? That is D naught. So a large voltage will be required to switch. So when the switch closes, the air gap, I mean, I have already applied a voltage of say 5 volt. That 5 volt will appear across a piezo resistor that I have put, a violet color one, a piezo resistor. Okay. So now you see, this is the exact diagram. The supply voltage is here. The CP1 and CP2, these are the two contacts. When the switch collapses, the CP1 and CP2 will be closed. And you will get a voltage across CP2, the resistor. So this is the top view of the diagram, bottom diaphragm. So when the pressure is increased, you see, now I am showing what is the working mechanism I am showing. See, now the first case you see, now the pressure is zero. The pressure is zero. So now the switch has collapsed at a particular voltage called pull-in voltage. That is very close to the peak of the ramp voltage. So the switch will be closed only for a small time. So the pulse width will be less. Now when you apply a large pressure, now the air gap will be less. The switch will collapse at a lower pull-in voltage. So now you see what happens. The pull-in voltage is somewhere in the middle of the ramp. So the on time will be high. So now you see, I don't use any other electronic circuit, but I am with a simple switch and the diaphragm, I am able to convert the pressure into a change in pulse width. That is the beauty. Okay. These two diagrams, if you have understood the concept. First concept is the RF switch pull-in voltage will be large if the air gap is more. First point you have to understand. The second point you have to understand is when the pressure is more, the air gap will decrease, so pull-in voltage will be less. These 2 points, if you have understood, you tell yes.
Yes, sir. Understood, sir.
Understood? Okay. Basically, if it is a classroom, it would be very easy. Since it is online, we don't know what is happening. That is why I'm asking. Okay. First of all, try to understand this concept uses not the conventional concept. I am going to use a RF MEMS switch with conventional MEMS pressure sensor structure to get a digital voltage directly. That is the concept. So, what you need to understand is what is pull-in voltage. For a RF switch, the RF switch is basically a cantilever beam, and the substrate downward, that is a fixed place. Now, when the RF voltage is given a power supply, when the voltage is more and more, there will be electrostatic field. Now that electrostatic field will be very high, so the beam will be moved or attracted downward, because what I have in the down plate is negative voltage. The top plate is positive voltage. When the field is more and more, it will collapse. So when this collapses, it will come in contact with the contact. Already I have made contacts. So it will connect the supply to the load. So that is the concept of a switch. The RF MEMS switch will collapse and will make contact with a particular contact pad when the applied voltage, when the actuation voltage is more than the applied voltage. So now second point, the pull-in voltage is directly proportional to the air gap. If the air gap is more, I need a large voltage for the switch to close. If the air gap is less, I need a small voltage for the switch to close. Okay. So now here I am using the diaphragm as the diaphragm will deflect upward when the pressure is changed. So now what will happen is, when the pressure changes, the diaphragm will deflect upward, so that air gap will change, so the air gap will decrease, so pull-in voltage will decrease. So when the pull-in voltage is reduced, now I will be getting the output for a larger time across the resistor. I have already put a resistor across the switcher. So the circuit that I have formed is something like this. See, equivalent circuit. Do you see the equivalent circuit? So the CP1 and CP2, that is the switch. So when the switch closes, the supply voltage will come across where? Across the resistor.
Resistor.
So, across the resistor. So when the voltage comes across the resistor, now if the switch closes earlier, I will get the voltage across the resistor for large time. So pulse width will be more. Otherwise, pulse width will be less. So now the pulse width will depend on the pressure. Okay. So that means I have converted the pressure quantity into pulse width. Into pulse width. So that is the concept. Okay. So now you see this structure, you will understand the various components you have to understand. So what I have in the top is the RF MEMS switch. And I cannot apply the actuation voltage directly on that. Only over a particular area I have to apply. So what I have done is I have insulated it, and only in that area I am applying. And here you see there are some 3 contacts, CP1, CP2, CP3. So when the switch collapses, the CP1 and CP2 will get connected. So there I have put a resistor here. So the voltage VCC say 5 volt, that will come across the resistor whenever the switch is closed. And how long the switch will close, that depends on the pressure. So that way, I have converted pressure quantity into a proportional time, pulse width. Clear? So now, we know that I have converted the pressure into a pulse width. So that means I have to find out what is the relationship between pulse width and pressure. So then only I will be able to quantify the pressure. Pressure versus, now that means now in the whole thing, what I am doing is I am converting pressure into pulse width. Okay. So if the pressure is small, pulse width will be less or more. If the pulse width is less, pressure is small or large. You see this diagram and see. The first one is showing for no pressure. Large pressure means pulse width high. So pulse width is directly proportional to pressure or inversely proportional to pressure. One of you can tell. If the pressure is high, air gap will be less pull-in voltage. So switch will collapse early. The pulse width will be more. So small voltage means small pulse width. Large voltage means large pulse width. So if you plot pressure and pulse width, it will be a linear curve like this. It will be linear or non-linear, that we have to see. So that is why I am trying to derive the equation for the relationship between on time and pressure. Now you see here the deflection of the beam. How much time I have now? 10:52. So half an hour I have. Okay. Okay. So now you see this is the diaphragm. The brown color one is the diaphragm. So when I apply a pressure, the diaphragm deflects by a distance of delta. So the delta is the mid deflection, midpoint deflection. So the delta is given by this equation C2P. So the relationship between delta and P is a perfect linear. Okay. Now the next equation you see, I have a switch, RF switch, MEMS switch, and I am applying a voltage in the actuation pad, and now the pull-in voltage is directly proportional to the D naught. D naught is the air gap. So the air gap is directly proportional to D naught power 3/2. Okay. So keeping the constant C1, 8K 27 epsilon naught A, I am saying it is what? C naught D naught Q. So pull-in voltage is proportional to D naught power 3/2. Okay. So there, pressure is directly proportional to the deflection. But now here, the pull-in voltage is directly proportional to D naught. So if the air gap is more, the pull-in voltage is more. Now what I am going to do is, when I apply a pressure, the air gap changes. So initially it was D naught. Now the deflection is delta. So the air gap is how much? D naught minus delta Q. So now the delta, delta is equal to C2 times P. That already we have seen. C2 times P. C. So D naught minus delta, I can write it as D naught minus C2 P power 3. So now the T on, I can write it as what? T minus T times V pull in by V max. So that I am writing it from this figure. Total time period is T, on period is T on. So you need, if you think, you can write like this. T on is equal to 1 minus T on by T into V max. V max is the maximum voltage of the ramp signal. So now the pull-in voltage is directly proportional to T on. Okay, pull-in voltage is directly proportional to T on. So now I have the relationship between V pull-in and T on, and V pull-in, again, it is a function of the pressure. So if you put everything here, you see P becomes the function of T on. P is, see the duty cycle, let us say T on by T as the duty cycle. So P is given by 1 by C2 D naught minus 1 by C1, 1 minus D square. So there is a relationship between P and D. D is the duty cycle, or T on. So there is a relationship between P and D. D is called D on. T on, T is constant. So D will vary only with T on. So the pressure is proportional to T on, but not linearly proportional to. It is a complex equation. You don't know whether it will give you a linear relationship between P and T on. So that is a critical thing that you need to understand, because any sensor you take, the linearity must be good. So what now here for this equation, the linearity, we have to plot and see how the linearity will be. Okay. So now I have plotted the pressure versus duty cycle, because from the previous equation, I can write D, the duty cycle, is equal to 1 minus square root of C1 D naught minus C2P whole cube by V max. So now when I have plotted this, you see we have done regression analysis, and the T naught, I mean the pressure is converted into pulse width, and the relationship seems to be very, 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 very good. Especially now you see the first graph, I have plotted it for 0 to 450 kilopascal. So there the linearity is R square, you are getting 0.9917. So it is good relationship, good, you know that if the R square value is 1, then it is perfect linear. Regression analysis, when you do, if the R square value is 1, it is perfect linear. Here R square in the 0 to 200 range, you see it is a perfect linear relationship you are getting. So this equation, even though it looks like the D is non-linear, over a particular range. Now you see what you can do is, you can design the pressure sensor for 450 kilopascal, but use it only for between 0 to 200, then you will get perfect linearity. Okay. So now the pull-in voltage is again a function of the K. You see here, V pull-in voltage is a function of K, that is the stiffness constant. So when you design the pressure sensor, now the stiffness constant of the beam, that must be fixed. So you need to find out some equation for the stiffness constant. So I'm going. So this is when I apply a voltage over the switch, you are getting the deflection of the beam. So the deflection will be depending on the force you apply and the stiffness it has. If it is very stiff, then large force you apply. So the K is given as F by delta. So if the stiffness constant is very high, even for large force, there will be only small deflection. So the stiffness constant is a key factor that we need for the design of the particular switch. So we derive this by using conventional method, applied mechanics method. So here I am applying a uniform load exactly at the area between L by 3 and 2L by 3. Okay. So in the center 1/3 of the region. So now we know K is equal to F by delta. So I am going to calculate the equation for delta. So this, if you don't understand, don't worry. It is bending moment diagram, that is applied mechanics concept. So we are deriving the applied mechanics concept and we are calculating the delta. So the delta is equal to WL to the power 4 by 47.41 EI. So the L is the length of the beam. So W is the applied force, load. Okay. So now, how to fabricate this pressure sensor? How to fabricate this pressure sensor? That is very important, because formulating a idea is okay, good, but how will you realize it practically? So we will see how the fabrication process flow goes. So now the sensing diaphragm is fabricated by bulk micromachining, whereas the cantilever beam is manufactured by surface micromachining. So you might have already heard about these two techniques. Bulk micromachining is a technique in which we remove things by etching to get the realized structure, whereas the surface micromachining, we add layers and process them to get the required structure. So now in this pressure sensor, we need to use both bulk micromachining as well as surface micromachining. So this is the final structure that I need. Now I am taking a substrate, silicon wafer. So this is basically a SOI silicon, silicon on insulator. So the gray color one is the handle wafer, and the brown color one is silicon dioxide, and the blue color one is actually the diaphragm. That is the device silicon. So I am taking this wafer. Now I am oxidizing it. So the both sides will be oxidized. So now what you do is, I am going to realize the polysilicon resistor, that is our load resistor. So I am depositing polysilicon over that. Now when you pattern this polysilicon, you will get the resistor realized. So you have to dope it accordingly to get the polysilicon resistor. Now over that, you have to take contacts, metal contacts. So here in our study, we have used molybdenum. So the molybdenum beam, you have to deposit and then pattern it to get the contacts established. So now you see the contacts. The resistor is having two contacts. The last one will be connected to ground. The first one will be connected to the VCC. So you will get the contacts established. So now I am going to deposit the beam. So now surface micromachining, we know we need a sacrificial layer. So I am applying a sacrificial PECVD oxide, and over that again I will deposit, I will pattern it to get the anchor portion. Now you deposit molybdenum and put molybdenum you deposit and pattern it. Now over the molybdenum, I have to realize the actuation pad. So I will put again silicon nitride. So over that again I will put molybdenum to get actuation pad. So now if I remove the PECVD oxide, I will get the final structure. So before that, I have to do bulk micro machining, bulk etching of the silicon handle wafer to realize the pressure port. So now I have the final structure of the device. So now design of the PWM pressure sensor, that all depends on how you design. So the diaphragm side length, diaphragm thickness, cantilever beam length with the thickness. So these parameters must be designed in such a way that we will get maximum sensitivity and minimum non-linearity. So that is what is being done here. Okay. So here I have given some concept how to get maximum deflection and maximum sensitivity and minimum nonlinearity. Okay. So you can we have published a paper on this. So based on that, I have written these points. So based on these concepts, we have designed the side length of the diaphragm to be 500 micron, thickness of the diaphragm 5, length of the beam 1000 micrometer. So you see, ultimately you can see that the size of the chip will be only 2 mm by 2 mm maximum. 2 mm by 2 mm, you get a pressure sensor. Okay. So now here we are seeing the pressure versus deflection. So for 20 kilopascal, I am getting a deflection of 0.9 micron or something. So the linear relationship between pressure and deflection, it is perfectly linear. So now from the linear, from the deflection analysis, we can calculate what is the pull-in voltage because pull-in voltage depends on the air gap. The air gap depends on the total distance minus the delta. So now you see here, as the pressure increases, pull-in voltage decreases. So initially for zero pressure, pull-in voltage is somewhere around 2.5 volt. And for 20, it is somewhere around 0.5 volt. So I have given the thing for two devices. So we get perfect linear relationship. Pull-in voltage reduces as the pressure increases. Now I am converting this into average voltage. Average voltage means now if you take a square pulse, the average DC voltage will be the duty cycle multiplied by the V. So we get almost a linear change in the voltage with respect to pressure. So now we have analyzed it. Now we are getting a sensitivity of 80 millivolt per kilopascal with a regression coefficient of 0.9987. So that means the device can give a high sensitivity with linear relationship, linear output. That is critical. So now let me show you some simulation experiments. So this is the switch that was created, and this is the diaphragm. So when the pressure is applied, you see that the deflection changes. So you increase the pressure, the deflection is also increasing. Now, I have given the air gap for various pressure. So from that, we are calculating the pull-in voltage. And the pull-in voltage, you see here, this is the simulation results. The pull-in voltage decreases as the pressure is increased. So now you see here, this is the diaphragm deflection for various pressure. So every time you increase the pressure, the central deflection increases. That means now the air gap reduces. So this is the pull-in voltage versus pressure. So now on-time calculation, minimum voltage 2 volt, maximum voltage 5 volt for the ramp. If you do that, we get on-time calculation of say 10 milliseconds to 50 milliseconds. It varies between 0 to 450 kilopascal. So the pulse width changes from 20 millisecond to 50, 60 millisecond. So it is almost linear. So from that, we can relate the pressure with the on time. Now, finally, I told you that it has to be converted into, it has to be transmitted. So what we do is the output from the pressure sensor, that is pulse, so that we are modulating with a digital signal and we are transmitting. So in the receiver end, you put a low pass filter, get the signal again, use a counter. Now you see this circuit is going to be in your dashboard. So your sensor is not going to take any power, almost zero power. So the sensor battery consumption will be very, very small. So I have just given you some calculations. What will be the resolution if I use a digital counter? So the high resolution you can get if you use a digital counter for counting the pulses. So now we have fabricated the molybdenum beam cantilever beam. Let me just show you some pictures of that. The sensor has to be actuated continuously. So that means the cantilever beam will move and up and down continuously. So you need to develop, select a material of high quality and high strength. So we have used high Young's modulus, high conductivity material, that is molybdenum. Okay, so that is the reason we have chosen molybdenum. Now these are the marks that was used for making the molybdenum beam. So this is the fabrication flow. Initially it is a soy wafer. So over that you do thermal oxidation. Now you put photoresist and pattern it. Now you apply, you deposit molybdenum. Now you remove that, you will get molybdenum deposited, contact molybdenum. So over that again you put a sacrificial layer and then again photoresist. So pattern it. Now you deposit molybdenum. So you will get the molybdenum cantilever beam. So this is the process flow, and the switches has been successfully released. So what you see here is the released SEM picture of the released switch. So you are able to see, I think, the switch is real. What it is, a standing cantilever beam. You can see here. Okay, so do you see a cantilever beam here? So that is the SEM photograph. Of course, the in the intersection point, it has some issue that is due to some fabrication flaw. So that and all has been now corrected. So you can, using this method, now we have created, or we have realized, a molybdenum beam also. So I think so there are some failure mechanisms that we have studied that I will skip. Now, this PWM based pressure sensor can be realized using a fixed to fixed beam also. So this will have more reliability. So if you want to improve the reliability, instead of the cantilever beam, you can go for a fixed beam. So the same concept. Okay. You see here. Now it is a fixed beam. So in the fixed to fixed beam also, the pull-in voltage depends on the air gap. So we can get a pulse width pressure changed using this concept. Now major advantage here is the friction will not occur. In case of a cantilever beam, now there is a possibility, since only one side is fixed, the free end will collapse on the substrate and it will not release. So that is called friction. So if the friction, if you want to avoid, you can use a fixed beam. Kavita? Kavita? I think I have completed. Now,
Okay, sir.
so 10 more minutes is there. So if somebody wants to ask some questions, they can ask.
Okay, sir. Okay, sir. Participants, if you're having any questions, please ask. Sir, excuse me, sir.
Yeah,
Yes.
tell me.
Sir, why we are going for molybdenum, sir?
See, that is why I said molybdenum, generally aluminum, gold, that is used for uh, making contacts for in all electronic circuits, integrated circuits. Aluminum is the uh, aluminum is widely used. Gold is also used. Now, in this case, we need the cantilever beam will be continuously moving up and down. So when the so due to what, after some time, due to fatigue, the material should not fail. So you need a high strength, high Young's modulus, at the same time high conductivity material. So molybdenum is chosen for that.
Okay, thank you, sir.
Okay.
So dear participants,
You can use even gold, aluminum, no problem. But the reliability issues, that will be the main criteria.
Okay, sir.
participants, you can interact with sir. Sir, thank you, sir. Thank you very much, sir.
Okay, thank you.
Somebody is raised a question like
One of our participants, Visalashmi Ramasamy, has raised the question, sir. Can
Ah.
we use such fabricated sensors to study pressure in ground?
Ground in the sense, suppose imagine you want to measure air pressure, it is possible.
Sorry, sir. It is for measuring the groundwater, sir, like pressure inside the soil, the moisture inside the soil.
Inside, you have water flow in that.
In soil, like piezoelectric kind of pressure sensors are used to measure the soil moisture, sir. Can we
Moisture,
fabricate one such? Yes, sir.
that is for moisture measurement, no?
Like there will
From
be
pressure,
pressure in soil water also, sir. So groundwater pressure.
but what see the thing is, if the this, groundwater means moisture means it is already with the soil. It is not just water, isn't it? So how will you the diaphragm? The pressure has to be applied on the diaphragm. So how will you do that?
Okay, sir.
Sir, any questions? Sir, the participants and all, they have understood clearly, sir. That's why they didn't raise any question.
That is okay. Even if they don't understand, that is possible. If there is a possibility that people don't understand because, but you can read my papers. There are some 2-3 papers in uh, Microsystem Technologies journal. So you can read that. It is not necessary that everybody has to understand that because suddenly you come with a new technique and tell how this is, immediately you may not understand. So if you don't understand, don't worry.
Yes, sir.
But you can, idea you have to get.
Yes, sir. Thank you so much, sir. Thank you so much for accepting my invitation and wonderful talk on this particular topic, sir. I think we gained a lot of the participants gained more information from your speech, sir. So
Okay, thank you very much.
thank you, sir,
So
so much, sir. Thank
thank you
you.
very much. All the best.
Thank you, sir.
Okay.
We welcome you all back to the 8th session of this FDP. Now I introduce the chief resource person of this session. Mr. Sripadi Raja completed his master's in electronics from Bangalore University in 2007 and PhD from NIT Kesuvatkal. He started his career in MEMS as a project assistant in IISc. Later, he joined Big Tech in 2009 as an application engineer. He was a senior application engineer after the IntelliSense software team set up a new company, Sri Dutt Technologies Private Limited. He has conducted many training programs and has given many invited talks across India. He is associated with IntelliSense and its associated business for 11 plus years in representing India. He is now operating in the capacity as Manager Global Applications and Sales at IntelliSense USA. Sir, I hand over the session to you. Please, sir.
Yeah, thank you, madam. Am I audible?
Yes, sir, you are audible.
Okay, yeah, thank you. So, hello everyone. I'm Sripad from IntelliSense. With the assignment that we have today is up to 1 o'clock. So, to start with, most of you might have heard about IntelliSuite software, and some of you might have also used the software also. Okay, so keeping in mind about introducing the software to the beginners, so we can discuss and we'll be presenting the session, the capabilities of the software. And it was also planned that the session would be more hands-on, but again, also it is important to make, I need to make an announcement that if we have a hands-on session in 1.5 hour slot or a 3 hour slot, it is extremely difficult to manage it virtually. Okay, we have done many hands-on session in person. Even we have done it even in Annamalai University. Dr. Joseph Daniel had organized it long ago. We have done many times. So handling it virtually in this slot is extremely difficult. Okay, so for you to, but it does not mean that you will not get the software access. You can always request for an evaluation license for a duration of 15 days. And whatever is intended for the hands-on session, those materials will be provided to you for it with a duration of 15 days of trial license. Okay, so you can explore it using the video tutorial at your convenient time. You're doing that slot. Okay, and the software is not given now for the session, so it will be more of a presentation about the software and its capabilities. Okay, yeah, so I hope I've clarified the intention of the session now. Okay, let me share my screen. Is my screen visible?
No, sir, it's not visible, sir. Now it's coming.
It's appearing, right? Okay.
Yeah, yeah, sir.
Fine. Okay. Okay, so should we go ahead?
Yes, sir. You can proceed.
Okay, fine. Okay, so as I mentioned in the beginning, most of you might have heard about the software IntelliSuite. Some of you may have also used it, okay, at different levels of your requirement. Okay, and to start with for the today's session, so I'd like to start from the sensor and some 2-3 minutes about the sensors and also why a MEM sensor and its advantages and disadvantages. Keeping in mind about the research, what are all the challenges that you face in the design is what we'll discuss, and then we'll look into the structural design and how do we optimize the MEMS device using the software, and some research opportunities is what we will see. Okay, and later we'll talk about the IntelliSense University partnership programs also. Okay. Yeah, so typically in the device, so we have the mechanical compliance. Okay, I think I have hidden some of the slides. So let me enable them. I think I have written it. Yeah. Yeah. Okay. Fine. So I think I'll go ahead from here. Okay. So why a MEMS device is required? It's a device where it integrates with a sensor and an outside electronic circuit where it makes an interface between the two. Okay, it is small in size, it's low power consumption, lightweight, low cost, and it is portable. And once the process recipe is set, we can do the we can reproduce these devices, and then excellent control of material purity is seen, and then we can have a precise control of dimensions, and it can integrate with multiple functions along with electronic circuits. Okay, so there are some successful MEMS devices that is available in the market. That is the MEMS accelerometer, the gyroscope, and the MEMS microphone. So these are at a consumer level, at consumer electronics market. This has already seen its place. So there are means of actuations where it can be actuated using thermal forces and piezoelectric crystals, electrostatic forces, magnetic force, and hydraulic force. So MEMS as such has two parts. Like one is the sensing part and one is the actuation part. So here we have this. The actuation can be done with various forces, and these are some of the forces that we use. When it comes to the design of this device, here we have the mechanical optimization, thermal optimization, and electrical optimization. So since it's a coupled device, okay, it's a coupled device, meaning it can be thermal mechanical, it can be thermal electrical, or electrical mechanical. So it has multiple functions. So we start with a design requirement. Any design, whether it's MEMS or something else, we start with a design requirement, and basic design we do, and then we do the process, and then we do the process optimization. When we talk of IntelliSuite as such, the method that we adopt is the 3D CAD model, and then we have the TEM, that is the thermoelectromechanical, which is the multiphysics simulation tool. And then we do the reduced ordered model simulation to verify the FEM results and also the Lagrangian model. So this reduced ordered model will also lead us to connect other EDA tools like Cadence, Mentor, and MATLAB Simulink kind of tools with IntelliSuite. Okay, and then system model extraction and system level integration. Once these devices are finalized in design, then we have the layout. Okay, so we create the layout in blueprint module, and then we do the process optimization, we fabricate, and we do the testing. So this is the complete cycle of your MEMS device, how we adopt in the package. Okay, so here, if we go down further, we have some of the challenges. So like these challenges are there in the FEM simulation, and then the approach that we adopt here is the 3D CAD model, and then we can optimize the structure. Okay. Apart from this, you can also bring in the fabrication model, the device which is fabricated. So that's the novelty that we have here, that the fabricated device, like the fabrication simulation, the design done using the fabrication simulation can be brought into the FEM simulation. So that gives a more realistic results closer to the fabricated device in case if you fabricate. So we have a very less error margin between the working of the device and the device which is designed using the fabrication simulation approach. But apart from that, those who are working only on the multiphysics, so you can also have the design done using the 3D CAD models, and then you can still perform those simulations. Once assume that we have done the simulation and then we want to take it to EDA tool. We have a module called in simple where it can do a system level simulation. It can do the element based modeling and then the MEMS plus ROIC. Then it can do the system model extraction, reduced ordered model, which connects MEMS plus EDA. So which is MEMS plus EDA means that the sensor, whatever we develop, needs to interface with outside electronic circuits. It is just like our sense organs will work, or it has its significance only if there is a brain. Okay, if brain processing is bad, then whatever the sense organs that we have is of no use. Okay, so just like that, any sensor that we develop, a signal produced by these sensors needs to be integrated with outside electronic circuits in the proper format. Okay, so to make the signals readable. Okay, so that's essential. Okay, once all of those multiphysics part is done, we have the process optimization. We create layout, we define the process recipe, and then we do the optimization based on the simulation process. And then that helps in building the appropriate mask file, and we can perform calibration as well. Okay. So when we look into the challenges that we see in FEM model and design, this is purely for people who are working only on the multiphysics. They are least bothered about the fabrication module or the fabrication process. Okay, so for them, we have an approach that where you can use a 3D CAD model, and then you can do the FEM simulation, and then you can parameterize the input variables. So you can parameterize the structural, you can parameterize the input variables. So you want to do a parametric simulation, not just the input variables, but also the design. Like I take an example of a cantilever beam. I want to see the displacement for 1 Newton of force that I apply, and then what will be the displacement for a micro cantilever beam of length 10 micrometer to 100 micrometer. So you can increment, you can feed in the values in such a way that its length keeps increasing and the software keeps designing it. So you can parameterize the structural, okay, and you can parameterize input variables. So that is a sweep analysis. And then we have the system model extraction and reduced ordered model files. So to do faster simulations, especially when it comes to transient simulations, it consumes a lot of time. So for such simulation, we recommend you to use a system or to perform system model extraction and then perform the reduced order model, so that your transient simulation, which takes hours together, reduces to less than a minute. Okay, so that's possible. And then when we look into the element-based model, we also have an approach where you can do the element-based models, like the PSpice netlist kind of a netlist is there, where you can drag and drop these elements, and then you can create the structural model. So you can even parameterize the structural and also the input variables. So you can also consider that this is element-based model with in verification with your FEM simulation. So both can be used. And when we look into the challenges of the design, the process model, so what we do is the layout creation, the process recipe, and process integration. Many of us, in my experience in India, is that many think that multiphysics simulation does many things, and then whatever the result that we get is near to the realistic approach. But that's not the case. Okay, multiphysics simulation, the device dimensions, everything are in ideal case. Okay, so some of you, if you have fabricated any device, so you must be understanding the challenges to fabricate the device. Okay, so somewhere when we design 8 micrometer width cantilever beam and do perform a very novel simulations and come up with novel approaches in simulation, but when we really want to fabricate them, to achieve 8 micrometer width. I'm taking an example. Okay, so to achieve a 8 micrometer width cantilever beam, there are multiple processes that gets involved. Okay, many times we fail, and it can be 7.92, it can be 7.93, so it can be 8.01. So the realistic device when we fabricate is completely different. So those simulations can be done here, and you can bring in those models into the FEM simulation. So that's more important, and that will give us more realistic simulation approach and results. Okay, it's not just the 3D CAD model we design and then we simulate and bring in novel simulation results. Okay, it's important to incorporate the fabrication simulation and also do this. But on the other side, those who wish to do only multi-physics simulations, you can still create 3D CAD models directly, and you can still perform the simulation. So both provisions are available. Okay. So here, the solution that we approach for fabrication-based simulation model is, and also to create the device, we have a method called design rule check. Assume that in your project, you have a plan to fabricate the device, then you have your own design rules based on the foundry where you fabricate. So you can ask them, if you have decided to fabricate the device, and then you want to ask them what are your design rules. So any foundry would give them their design rules. Okay, so those design rules are provided to you, and based on the boundaries of the design rules, you can design your device so that that foundry can fabricate your device. Okay, so this it's possible, and you can do the process verification with the foundry where you fabricate it. Okay, so as such, on the design part of it, we have top-down approach, and one is the bottom-up approach. That is, the top-down approach is the element-based model, and then with the bottom-up approach is the fabrication simulation-based models. You can design in both ways. Okay, so in whatever way we design, we do a multi-physics simulation. So we do this FEM and BEM, finite element method, and boundary element method on a 64-bit multi-core processor. So you can do a parallel processing simulation also to fasten your simulation. And we have the boundary element method, and we have pre-corrected FFT and many advanced features to fasten the simulation. So finally, we can also create a Lagrangian model where the simulation can become 1,000 times faster than FEA. So that's what I was calling it as the reduced ordered model. Many of the well-known FEM simulation tool have this feature called reduced ordered model. Okay, so many call it in different names, but again, the concept remains the same. Okay. And some of the examples that we have is thermal electrical simulation, and we have linear and nonlinear models, and we have the thermal packaging analysis can also be done. Okay, so here the advantage of doing a reduced ordered model simulation is you can integrate your MEMS device with outside electronic circuits. So you can see this. Okay, so this device, what you see is a resonator, which is the system model extraction is done, and then put it on the black box where it can perform reduced order model. So this MEMS device can be integrated with outside electronic circuits, and to perform all of these simulation, you don't have to depend on any other tool other than IntelliSuite. Okay, so some of the tools do provide dependencies on other EDA tools, so you need not depend on that to perform this simulation. Okay, and the benefits that you get is if you are focusing only on the multi-physics simulation, is you can do a 2D and a 3D models, and we have a pre-processor module to do the simulation settings. Okay, this pre-processor helps in setting the device, the parameters for the simulation for large devices. Okay, large devices meaning when we perform array-based simulation, like micromirrors or microphones and pressure sensors sometimes are used in array form. Okay, so to perform such simulations, we use this preprocessor, and we can save a lot of time doing the parametric simulation, parameterizing the geometry, parameterizing the input variables. Okay, and the post processing is done using the visualize, and then we can have the macro model simulation, that is the reduced ordered model simulation. Okay, and moving on to the element based models. So we have these elements like beams, combs, plates. Okay, and you can drag and drop them, and you can perform, you can do the design of the MEMS device, and you can perform this system level simulation also, and the results are viewed on the 3D scale. Okay, you can drag and drop those elements, and then you can perform this simulation. So once you design it, either in any element based models, you can convert the same file to the layout file and also to FEM models. So you don't have to really do the FEM models again to perform the FEM simulation. So it can convert element-based models to layout and also to FEM models. So you can see that MEMS plus EDA is, you can integrate MEMS with electronics controls and digital structural mechanics thermals. So you can control with the outside electronic circuits. The benefits of using the the system model extraction is that we have a schematic driven design. We have a hierarchical modeling, which saves a lot of time. Okay, and then the design exploration is done with multiple designs, which are much faster, and then we can view the results on the 3D scale. Okay, so that was on the device simulation. So if you are a fab engineer or you are dedicatedly working on a clean room setup, so then you must be performing deposition, lithography, and etching and bonding. So these are the four major steps with different materials that people do in foundry. Okay, here we have the FEM simulation where we can parameterize the structural and parameterize input variables. So here, let me go to the fabrication simulation directly. Okay, let me skip this part of it and then come back later. So here we have a template-based design, for polymums, SOI mums, piezo mums, screen summit. So we already have it. And typically a MEMS process is a custom-made approach. You can also design your own PDK also. Okay, we have extensive material database, and then we have the process traveler where you can export this to other file formats like Excel and PowerPoint. Okay, so here a process template is SY process, and also the custom-made approach is also possible. So when we do a custom-made approach, you can see that you can define your own process flow to define the fabrication method. What you see on the right side is an optical waveguide simulation. So we are performing multiple DRI and isotropic process. Okay, and this is the custom approach, the custom process flow that is designed. Okay, and when you are working on silicon-based devices, then we have the fabrication process flow, like the isotropic etching is performed to attain certain shape, anisotropic etching is performed, and plasma etching is also performed for getting straight cut. So different profiles of etchings are required for different applications. So you can perform them. So as I mentioned, if you are working on the clean room, so then you can see that using different combinations of chemicals, like for wet etching, you use KOH and you can use IPA. Along with that, KOH, we have IPA, and then we have TMAH. For typically for electronic circuits fabrication, we use TMAH, and then sometimes to achieve smoother surfaces, we use Triton as a which is a surfactant along with TMAH. Okay, so different combinations of chemicals provide different profiles. So if you are dedicatedly working on wet etching, then use this simulation tool to optimize your mask to achieve the desired shape when you really fabricate the device. Okay. So one typical example I want to show you is that people who are working more on multiphysics simulation, so for them, and also those who are working on clean room can understand it better, that the mask shape is can be completely different to achieve a desired profile. So here on a silicon 100 wafer, we use a plus shape mask to create an octagon structure. Okay, so it's not that the mask shape is octagon, the mask shape is in the plus shape, but we are trying to achieve that using this, we try to achieve an octagon shape using the plus shape mask. Okay, I'm not saying that plus shape mask is having a larger advantage. I'm just trying to tell you that the mask optimization is very much essential when you are doing your fabrication of your device. Okay, so for those who are working in clean room and also those who give the designs to the clean room for fabrication, both needs to understand that the mask preparation is a challenging task, and that can be solved um, using this tool. So same octagon shape mask on silicon 111 wafer has a different mask orientation. You can see two different triangles connected to its edge. Okay, and then you can perform this simulation. So you can see that octagon shape is achieved on 111 wafer using a different mask profile. Okay, so here you can see that further etching leads us to a different shape. It becomes a 6 faces hexagon. Okay, 6 faced profile. So we wanted to do an 8 face, that is the octagon, but when we do a over etching, it became a hexagon. So it means that the time of etching that we set should also be optimized. So multiple of these factors are involved in the fabrication. So those things can be optimized using the software tool. Okay. So those who are working on optics know the significance of the material indium phosphide. Okay. And you can use this indium phosphide material to achieve the etching to get the desired profile. Okay. So you can do this simulation as well. And similarly, people who are working on quartz, so those who are working on a fabrication of quartz material, you can also use this tool to achieve the desired profile. Okay. Okay. So here, this is what it is. You can see the same mask on different cut, 80 cut, Z cut. So different shapes of mask are achieved. Sorry, different shapes of profiles are achieved for different masks. So you can see that based on the orientation of the quads, different profiles are achieved for the same mask. Okay. Yeah, so here let me show you the module part of it. So when you install the software, so here we have this package. So what you see is the package, okay, and then you can do your layout using the blueprint module. So if you are preparing a file like a GDS file or layout files or 2D layout files, so you can create them, okay, and you can see that you can create your own DRC, and then you can also get the 3D model from here. It also, okay, you can define its thickness and then you can get the 3D models also, okay. So that's possible, okay. Once you create the layout, we open a, we can push this module to create a 3D models, and also you can use this for fabrication process flow, okay. I think, let me use this. So this is an example of a piezo-resistive pressure sensor device, which is oriented towards 45 degrees. Yeah, so here you can see that the silicon wafer is silicon die is defined. We have a photoresistive material. We do the lithography and we do the boron doping. So you can see that from the cross-sectional view that the boron doping is not a deposition, is an implant which goes inside the device, inside the material. So boron doping is done, okay. So and this is what the piezo resistive materials are, okay. You can see its depth, its profile, okay. You can see the cross-sectional view in any direction, and then we have the resistors, piezo resistors. And this is an isolation layer. We deposit silicon nitride as an isolation layer so that we can get via contacts. So we need to connect metal to these piezo resistors, but it should not get connected to a substrate. So for that, we use this isolation layer of using the material silicon nitride. Okay. So this is the metal. So we have created the device. So you can see that the device looks like this. You can get any cross-sectional view. And then you can push the design for FEM simulation. So this is the device. So okay, so we have a package also. So we perform a package, do the lithography process at the back side, and then we can etch the silicon. So we get an isotropic profile. So I'm sharing it on the screen and also running the PPT. I think graphics is not supporting me. But anyways, you can push this design to the analysis. So I can push this design to the analysis. So here you can see I set the mesh. So for in the interest of time, I'm increasing the mesh. So you can also do the refinement of mesh here, and then you can mesh the design. So yes. think I cannot push this now. I think I have to close many of these programs to push this design. So anyways, I've already done it. Let me show that to you directly. Yeah, so you can see that this design has been exported. So here we set the simulations. So we set the simulation based on static, frequency, and dynamic. To perform the static simulation, we choose this. Frequency as this eigenmode values, and also the dynamic values, dynamic simulation, time based or frequency based. And then we do the macro model simulation for a reduced order model simulation. Okay. And then we set the material properties. In case if we have done the design using the fabrication process flow, then we don't set the material property. We need not do that. But in case if our design is done using the 3D CAD models, then we set the material properties. Okay. And then we input the loads based on the application, and then we have the boundary condition set, and then we have the mesh and analysis. Okay, so that's how we carry forward the simulation. Okay, at this point of time, I'd like to take a pause. Do you have any questions until now? Do you have any questions until now? Yeah, if you have issues with your mic, you can also post your questions on the chat box.
Dear participants, do you have any doubts? If you are having any queries, please ask, sir. Sir, one of our participants, Deepa, is asking, IntelliStute software is available in online. Is it available online?
Available online, meaning if you want to get the evaluation license, you can write to us and then you can get it. Okay, so it's not available for download online. So you have to request by either by email or in the IntelliSense website. There is a web form. You can request and then you can get it. Okay, any more questions or should we go ahead?
Sir, it seems no other question.
Fine. Okay, fine. I'm continuing my session. Okay,
Yes,
fine.
please.
So I'm sharing my screen again. Okay. So going back to the tool here we have this model that we create, and then we can push this to the analysis, static analysis of frequency or dynamic, and also the macro model simulation. So you can set the parallel processing also. If you have 32 GB, you can set 32. Okay, so sorry, 32 core processor, you can set 64. So based on your availability, you can set. So you can perform parallel processing simulation also. Okay, and then you can set up maximum physical memory, and then you can perform this simulation, and also you can visualize the output in Visualize for better graphical representation of results. Okay, so that's how the multiphysics simulation is done. Okay, when we look into the simple, that is the system level design and simulation. So here you can see that you can drag and drop these elements, and then you can perform this simulation here. So drag and drop, you can set those dimensions, length, width. Okay. So similarly, we have created an accelerometer using the element-based models like the plate elements and the beam elements and comb structures. Okay, so to create, how do you visualize this? In case if you want to see what is this, you can easily convert this to a layout file, and then you can see that this is the file that we have created using the element-based models. Of course, in the beginning, it would be difficult for you to understand. So, but with practice, you'll be able to make it. Okay. So this is the layout. This is the serpentine structure that we have created. And this is the file that we have created using element-based models. So similarly, you can push this model to 3D CAD model also, so that you can get the FEM model for to perform FEM simulation. Okay. So EDA, you can prepare a VHDL, and then you can prepare a VHDL file of equivalent of this one, and then you can integrate with other EDA tools also. Okay, yeah. So this overview in a simple, and here we have the EDA tool, that is the EDA linker, where we perform. Well, let me show you. Where the reduced ordered model file is exported to Verilog A or any other file that you or any other file format that you wish to work. So here I would say Verilog A, then we set this. So let me give it as test capacitive pressure sensor. So here you can see that a Verilog A file is generated. So Verilog A file of your MEMS device is generated. So you take this Verilog A file to the EDA tool like a Synopsys or Cadence like tools, and then you can open this for them. Okay, for further ASIC design, application specific IC design. Okay. Yeah, so similarly, we have module to perform the bed etching simulations. So here you can see that we define the substrate material, and then okay, and then we can deposit the mask. So you can perform the simulation. of wet etching. So I'll reduce the time in the interest of our session time, and then you can perform the simulation. So we generally think that such profile can such mask can generate the equal profile, but that's not the case. You can see that what is the profile achieved for performing a simulation where for 10 minutes. Okay, so using this mask, complete material is gone. Okay, we did not achieve any shape. Okay, so these things, these predictions can be made for wet etching and also for dry etching. Okay, yeah, okay. So we can also calibrate based on the applications, in case if we are optimizing it, then you can bring in the practical edge rates, and then you can perform these simulations so that you can optimize wet etching. Okay. So here the etch rates can also be set for different orientations of mask. You can set the etch rates, and then you can get the profile output. Okay, so you can see that when I set this, when I change the etch rate in 111 direction, the profile changes. Okay, so okay, so etch rates are typically the parameter which gives us the profile. So you can see the surface profile can also be extracted for various orientations. Okay, so here you can define 110, 111, and 100 orientation. So similarly, this is for um, KOH, and also that is for silicon and also for quartz. And recently we have introduced sapphire also. Okay. Yeah. Okay. So this is what you have, and then you can do the calibration using the wagon wheel analyzer. So let me not open that because I see hardly uh, people incorporate wagon wheels of late these days. So we had this module earlier. Okay, and now we have this module called job manager, where you can set the process, set the simulation sequence, like you are away from the lab for a few days or some 2-3 days, but you want to the simulation needs to be performed. So you can set the sequence of simulations using the job manager and leave it. So when you come back, you can get all the results output. Okay, so that way we can imp keep on the timing of the simulation. Okay, yeah. So here I'd like to take a pause again. So if you have any questions, so we can interact. Okay, so I can keep on going, showing you different features, but it would be more interesting in case if I can address any of your queries. Okay. So any questions?
Participants, if you have any questions, please ask, or you can type in your chat box.
Yes.
The Deepak Kumar is asking, how could we access IntelliSimulation software?
Well, if your institute already purchased the license, you can access through them, or else you need to purchase it. But for a temporary use, you can get a 15-day evaluation license. Any questions in case if there are any users of the software?
Sir, one more question. Could you provide me 15-day free trial version?
Yeah, that you can always ask. You can write to india@intellisense.com and then you can get the trial version.
Okay, sir.
Yeah.
Any other questions, participants? Sir, it seems no other questions.
No other. Okay, fine. Yeah. Okay. So here, when we want to perform parametric simulation, so you can see that you can parameterize the structural, like you can set the layer manager and you can see that the X, Y, Z dimensions, the length, width, and thickness dimension can also be parameterized. So when you parameterize such structure, it's easy for you to understand, or it saves a lot of time. Let me open this events and you can see. Probably, I think I have them in my slides itself. Let me go back to that. Yes. Yeah, so you can parameterize the structural. The advantage of performing parametric simulation is you can parameterize the structure and also the load. You can get the software can generate multiple 3D models and with one mesh, and then you can set the mesh element size, and automatically it applies the boundary conditions and gives a comprehensive, easy to interpret results, like something like this. This is an example of an accelerometer where you can see that the natural frequency of an accelerometer changes with beam length. Okay, and that can be seen with multiple values of parameters, like the example of a comb structure where we have a piezoelectric beam also. And here you can see that with there is a change in capacitance with overlapping electrodes in the case of comb structure. So in the case of piezoelectric beam, we have the change in XYZ displacement for increase in the thickness. Okay, so piezoelectric, you can perform inverse piezoelectric simulation also. Okay, system model extraction happens like this, like it captures the energy associated with each modes of vibrations and then captures the electrostatic energy and then captures the fluid damping characteristics and then packs it in a compact model, and then we give a HDL file. So when we have a HDL file, then we have the macro model simulation where you can perform integration with outside electronic circuit. So what you see here is not an electronic circuit, but it's a signal conditioning system where you process those signals to a readable format. Okay, you can perform mathematical operations on those signals so that it can be easily synthesized and made into a readable version. Okay, and we have a reliable results and benchmarking where we have finite element models, the system model extraction and reduced order model. Comparing these results, you can get more accuracy in the results, the FEM and the Lagrangian model, and the comprehensive study of the design, the structural behavior and behavioral study for a range of loads. So when we have such information, then we have more clarity on the device if we are targeting any applications. Okay, so for element-based models, as you can see, the same elements are being used to build various structures. Okay, like the cantilever beams are the beam element is used to build cantilever beams, the resonators, accelerometers, gyroscopes, okay, micromirrors, the same. So it all depends on what application are we looking at. So we can also perform parametric simulation using the element-based models, and then you can see that for various thickness, the amplitude of vibration changes. So the software can perform that, and also the ambient conditions. So when we are working at different environmental conditions, the device performance changes. So you can also set the ambient conditions and get the associated output. So the outcome is with FEM-based models is that we can perform the parametric simulation with we can parameterize the dimensions, the loads, and the material properties, and perform static frequency and dynamic analysis and get the results ideally. Okay, ideally meaning that either in only if we incorporate any damping factors, it incorporates those damping, but it does generally it does not have an inbuilt damping factor. So we have to define a damping factor there. But whereas in the case of element-based models, you can still perform those simulation, and then these simulations are based on ambient conditions. Okay. Of course, these ambient conditions are also set to a value of the default value, but again, you can change those values. There is a provision to change, but in the case of FEM, you have to give a damping factor. On the other side, for simulations involving like microphone, where acoustic pressures are involved, you can calculate the viscous damping factors. Okay, it's damping due to the air, the compressible fluid, and in case if there are any fluid structure interaction, the damping caused due to the fluid can also be calculated. So I think I've talked about the MEMS clean room part of it. So here I'd like to conclude my session to give an overview of what the software is all about. And unless I can still be available up to 1 o'clock, demonstrating some of your queries. Okay. Okay. So any more questions?
Participants, if you're having queries, please ask. Sir, in the last question session, one participant has asked software cost per license user.
That you need to write by email and then get it. So let's restrict our discussion only to technical terms. Okay, the pricing and other things can always be discussed over email. So please drop in an email to india@intellisense.com. So you have large discounts for academic is what I understand. By my colleague Sridevi would give more details about the pricing.
Dear participants, if you're having any queries, please ask.
Maybe any queries specific to the project that you're doing on MEMS. I think I can demonstrate building a case.
I said. Yes, please, Mr. Deepakuba. You can turn on your mic and ask too. If you are facing any difficulty with your mic, you can go for chat. So,
Yeah. So what was the query?
Would you avail the facility for project as collaborative work?
Well, that can always be discussed at is it academic institute? Uh,
Sir, you are not audible.
yeah, I think, am I audible now?
Sir, it's very feeble.
Oh, is it? Okay. I think there's some network issue then. Is it clear now?
Now it's okay.
Yeah. Okay. Fine. Yeah. Yeah. So, Deepak Kumar, I think any project related stuff, you can always again write back to India at Intelligence for any technical or any pricing information. So we can address it. Okay. But in case if you want to get more details, I think you can switch on your mic and then we can track also. Mr. Deepak Kumar, is my voice reaching you? Okay, fine, thanks.
Anyone else? If you are having any queries, you can ask. Okay, sir. We feel that everyone is attending very keenly and they are having no doubts or any queries.
Okay,
People have started
yeah,
thanking you.
okay.
Sir, have you finished all the slides you have?
Yes, whatever I intended once, I was wondering that I'll talk only for an hour and then probably address some of those queries because it was a hands-on session was planned and licenses are not being provided. Hence, I thought I'll demonstrate the case one by one based on the query. So, but there are no case, I believe. So, I think you can, from my side, I'm done.
Okay, sir.
Yeah.
Thank you so much, sir. Thank you for accepting our invitation and giving a lecture over here. Thank you for your
Okay.
patient answering. Thank you. Okay. It was very informative. Hope all our participants have gained some knowledge and information from you. Thank you so much.
Okay. So anyways, I'm available for the next 10 minutes in the meeting. In case if you have any queries, you can drop in a message. I'll be able to answer them. Okay.
Yes,
Thank
sir.
you.
Yes, sir. Please be.
Yeah. Okay.
Dear participants, sir, as you have heard, sir will be here for 10 more minutes. If you are having any queries, you can ask him. Sir, if possible, could you please give your mail ID in the chat?
I have given this email ID. So based on your query, the respective person will address. If it's technical, I would reply. If it is commercial, my colleague Sridevi would reply. Okay. So that's the email ID, india@intelliscience.com.
Okay, sir. Thank you. Hope our participants will note it.
Sure, Mr. Deepak Kumar. Please write to that email ID. We will certainly assist you on that. Okay, thank you, madam. I'll log out of the meeting. So in case if anyone has any questions later, you can drop in an email to india@intelligence.com. Okay. So thank you. Thank you, madam.
Thank you, sir. Thank you so much. Thank you for your patience too. Thank you.
Yeah. Bye.
Good afternoon, madam.
Sir, good afternoon, sir. Good afternoon, sir.
Yes, madam. Yes, madam.
Shall we start now, sir? Sir,
Yes, madam. We can start, madam.
Enough of participants, I welcome you.
Good afternoon, everyone. Welcome back to the post-lunch session of day 3. This current session will be engaged by Dr. S. Hosim Tilagar, who will deliver his talk on MEMS-based sensors. Before handing over the session to him, this is the brief information about him. Dr. S. Hosim Tilagar is a professor in Department of Electrical and Electronics Engineering, College of Engineering, Guindy, Anna University, Chennai. He is also the director of Center of Academic Courses, Anna University. He did his BE in Electrical Electronics Engineering in MEFCO Shillong Engineering College. Then he obtained his ME in Power System Engineering from Tyagarajar College of Engineering in 1994. He did his PhD in the field of electrical machines from IIT Madras. He has successfully guided 3 research scholars for obtaining their PhD degrees, and currently he is guiding 5 PhD researchers. He has published 19 research papers in international journals and has presented 14 papers in national level and international level conferences. The patent obtained for circular microgripper adds a star to his profile. Dr. Tilagar has successfully completed project worth around 1 crore from various funding agencies like CDAC, Baba Atomic Research Center, INUP, etc. His area of specialization include electrical machines and drives, electrical vehicle technology, and MEMS technology. Now, on behalf of Annamalai University, we will welcome you, sir. Now, I request you to deliver your lecture on MEMS sensors.
Yeah, thank you, Mr. Venkatesan. So I'm delighted for being called for providing a lecture in this faculty development program sponsored by AICTE, Atal scheme, I think, in sponsorship, I mean, in collaboration with Annamalai University, this FDP is being offered. So I am very happy to be part of it. And today I would like to discuss about some of the activities that we are currently undertaking. So that I would like to also say in the very beginning itself that this presentation, what I am going to make here, is directly not very much associated with MEMS sensors, but a cue can be taken from here, and MEMS related activity can be extended to this application what we are trying to develop actually. So of course we have done a few MEMS related sensors and actuators in the previous occasions of research, but this particular domain of research is not exactly MEMS related thing, but of course it has a lot of potential to it, I suppose. So now I will directly go into the presentation part, where I'm going to discuss about the field testing of soil and the soil nutrients, so that it will help the agriculture and farmers. That is the application that we have been working for quite some time, and I will present some of the aspects that we have explored in that area. So I am sharing my screen now. Mr. Venkatesan?
Yes, sir.
Yes, sir.
Once you are able to see my screen, you tell me.
Yes,
Surely, sir. Surely, sir.
Yeah. Are you able to see my
yes,
screen?
sir. Your screen is visible, sir.
Yeah. Thank you.
Okay.
Okay. So, as I said, today I'm going to talk about some of the explorations we have made so far on design and fabrication of soil nutrient sensor. So in this application, I'm going to talk about some of the sensing methods that we have considered, and we have boiled down to electrochemical sensing method, and we have developed a planar ion selective electrode system to test the soil nutrient. So that I will explain in this presentation. Wherever you have, if the audience have any questions, any queries, can stop me right there and ask those questions so that I will be able to explain then and there. Okay. So
Sir,
to have
sorry for
a
disturbing, sir.
yeah.
Sir, just to make it on presentation mode, sir.
Oh, is it? Okay, okay, okay. No, in my screen it is in presentation mode. Uh,
Mm.
1 minute, 1 minute. I'll do that. Actually,
Okay. Which option you selected, sir? Entire screen just to make it on, sir.
yeah, I have to go do the entire screen only. Should I stop screen and again do that?
Yeah, you
Stop
can do it,
sharing
sir.
and again do that? Okay.
Okay, sir. Okay, sir.
Actually, I have gone for entire screen only. So is it now entire screen?
Yes, sir. Now it is.
Okay, sir. Fine.
You can continue, sir.
It is
Yes,
okay
sir.
now?
It's okay now.
Yes, sir.
Yeah. Yeah, thank you. Fine. So now to have a few ideas about the kind of methods that are being employed to detect the soil nutrient. Before going into the methods itself, I would like to say a few words about the soil nutrients themselves. As we know, potassium, nitrate are the significant soil nutrients. Even sodium also significant soil nutrients. Besides that, there are so many number of micro level soil nutrients present in the soil. Now, when a farmer gets into the business of uh, having a crop in his own field, in general, in good old days, actually farmers used to, as we know, plough the land so that the soil gets upside down, so that the soil on the bottom, which is supposed to be nutrient soil, comes on the top. This is after completing a harvest actually. So this is normally done because the soil nutrient what was there earlier has been absorbed by the crop, whatever has been harvested as of now. Then for the second harvest, what the farmer is planning, he has to have the soil to be sufficiently having the nutrients. So ploughing is one of the methods to do that. But again, how to verify whether the soil has sufficient nutrients to feed the plant actually. So for that, so many methods have been developed to test the soil nutrient, but these methods are there in laboratories, and the farmer has to take the soil as a sample to the laboratory and wait for the result actually. Here two things are involved. One thing is the farmer has to take the soil and submit to the laboratory, which takes which consumes time, number one. Second thing, he has to pay a sum of money against this cost of the testing. And the cost of testing of soil also is not so cheap. It runs into a few thousands if it is a very high sophisticated laboratory, or a few hundreds if it is a relatively low profile laboratory. But whatever may be the case, time and money are involved. Now, the idea behind this kind of development, what is proposed, is that whether if we can give a soil nutrient tester on the hand of the in the hands of the farmer itself, so that the farmer will be able to do the testing by himself in the field itself. So he need not run around. He should have a testing sensor in his hand and he should be able to do it. Now, coming to the question of methods, as is shown in this slide, optical sensing is one of the popular method deployed in the laboratories, but it involves lots of money actually. Very sophisticated testing labs are there using optical sensing methods. Another one is electrochemical sensing that uses ion selective electrodes which generate a voltage or current output in response to the activity of selected ions. So the soil nutrients, okay, will have its own ions that it will release under the testing conditions, and these ions are absorbed and by the respective electrodes, and these electrodes develop a potential, and if that potential can be sensed, then it can be provided as a result actually. Coming to the electrochemical sensing method. So electrolysis is one of the popular method, as we know, deployed in good old days for kind of developing ion, attracting the respective ions towards the anode and allowing the current to pass through and measure the current. So either we shall provide necessary testing sample inside the analyte that is there inside the vessel, and this ion that is getting attracted towards the electrodes will in turn be converted into current, and the current passage will be measured in terms of amperes or the potential difference as itself, which is a sensing signal for the ion concentration inside the solution. This is a good old method, the electrolysis, and this same method is only being considered in our case also for the testing of the soil nutrient. Now, with regard to the kind of implementation of this particular method, that is the electrolysis for testing the soil nutrient, it is nothing but an ion specific electrode system as it is shown in this picture, where you will be able to see two electrodes. Normally in electrolysis it is anode and cathode, and here it is called a reference electrode, and another one is the ion selective electrode. You will be able to see them as you are seeing here. You see reference electrode on the left side and ion selective electrode on the right side. Now the reference electrode will be prepared, okay, with a particular material, and ion selective electrode also will be prepared with another material. And here on the bottom of the ion selective electrode, you'll be able to see something that is called ion selective membrane. Now, if you pour the sample solution inside this beaker, and the nutrient, whatever is available inside the sample solution, will release its ions, and because this particular electrode, okay, attracts those ions, and it is passing through a membrane, and that membrane is an ion selective membrane, which means this particular membrane will attract only that very ion which passes through it and gets attracted towards this electrode, and this electrode develops a potential. And that potential, if it can be measured and quantified, that tells about the concentration of the nutrient inside the soil or the sample. Now, this is a 3 electrode system, which is not really much different from the 2 electrode system what has been shown earlier. The only difference is that besides the reference electrode and the working electrode, it has also got one counter electrode. Okay, so as it is represented here, working electrode, surface where the electrochemical reaction takes place, And reference electrode, already I have explained what is reference electrode. Reference electrode is nothing but that electrode which has to provide a 0 volts potential always. So with reference to that only the potential difference is measured. And the counter electrode which supplies current required for the electrochemical reaction. Actually here it is a sort of potential divider kind of arrangement. Instead of measuring the entire potential between working electrode and the counter electrode, we have introduced one more electrode, and the potential between that electrode, that is reference electrode, and the working electrode is finally measured. So it is a kind of reduction of potential that is being taking place. That is the only difference between the previous 2 electrode system and this 3 electrode system. So the difference of potential has been brought down. The idea behind this is that to increase the precision of the measurement. That is the only idea. Otherwise, no real big difference. Okay. And this is an example of a thing what has been represented here. This is a glucose test strip. Of course, our application is not to test the glucose. This is only a symbolic representation that has been shown here. So you will be able to see that this is also nothing but a electrode type of strip. This strip itself is placed on the substrate, which can be of any relevant material, including silicon. And these electrodes, which is pasted or printed on top of this substrate, okay, will have 2 electrodes or 3 electrodes depending on the number of electrode systems that you are developing. And finally, you will apply glucose on that, and this glucose will be tested and quantified. The concentration of the glucose will be tested and quantified by this test strip. So similar to this, we also intend to develop a kind of soil testing this thing, which is almost developed now. And I'm going to further discuss about the implementation process of developing this kind of soil testing strip. Okay. Now coming to the fabrication part. The first step is the electrodes are fabricated using screen printing technique, and the setup is tested with EM stat. EM stat is nothing but a potentiostat. Okay, it helps to measure the potential difference between the electrode, and this potential difference, as I said, will be available as you pour the sample inside the analyte solution, and it releases the ions, and the ions gets attracted towards the electrodes, and it develops a potential difference, and that potential difference we are measuring. And coming to the reader circuit, the reader circuit is designed using node MCU. So it is a microcontroller chip which is used to do the programming part and read the signal out and pass to the necessary place wherever it is required. So now these are all some typical representations of the screen printed electrodes. So this is of course a 3 electrode system, as you are seeing here, a working electrode, a counter electrode, and a reference electrode. Okay, and this 3 electrode system, if it is dipped inside the sample, and of course the ions will get attracted towards the electrodes, and it will develop potential, and you will be able to read it out. This is only a symbolic representation. Of course, it is not the one we have developed. Actually, it is only a symbolic representation. Now coming to the question of representation of conventional and proposed ion selective electrode. Here, how to develop a ion selective electrode. Okay, how to develop not only ion selective electrode, also the reference electrode. So on the right side, what you are seeing is the representation of a reference electrode. Representation of reference electrode. So what the reference electrode is made of? It is made of silver, Ag. The reference electrode is made of silver, and if you dip inside a potassium chloride solution, then on the bottom it gets chlorinated. And this part where it got chlorinated is now becoming silver chloride, and it will be able to act as an electrode now. It will be able to attract the ions, and it will be able to develop some potential. So this is the thing, our representation of the reference electrode. And the same thing what has been shown inside a test tube, right? That reference electrode inside a test tube, what you are seeing here is implemented in this way. It is screen printed on a substrate, and what you are seeing here, is the electrode, and on the top it is a silver, and on the bottom it is silver chloride, as I explained. Okay, so silver chloride is the electrode part where the testing will take place. Okay, now similar to that, the counter electrode also will be prepared, that I will subsequently explain. And now you see on the left side in the picture, what you are seeing is nothing but an electrode here on the left side and another electrode on the right side. Okay, and there is a chemical membrane over here. This membrane will be able to attract the ions and pass it through the electrodes. Okay, now this shows the complete picture of both the reference electrode and the ion selective electrode. Ion selective electrode is another electrode. You see on the right side, what you are seeing, are you able to see this? This is RE, reference electrode, and this is WE, working electrode. Okay, reference electrode, as I said, will be prepared by the method I said earlier, that is using silver. And ion selective electrode is again produced with the necessary material that is capable of attracting the nutrient ions. So ion selective electrode is an analytical technique used to determine the activity of ions in aqueous solution by measuring the electric potential. The electrolyte in the working electrode is separated from the sample solution by an ion selective membrane. Here the ion selective membrane you are able to see here. Okay, this entire setup will be dipped into the sample solution, and inside the sample solution you will have the soil nutrient, and that soil nutrient will be attracted towards this ion selective membrane. Means this membrane allows the ions only that it will supposed to allow. That kind of membrane will be chosen, so it will allow only the nitrate ions inside or through it, and that will finally reach the working electrode. And more and more ions, if it reaches the working electrode, more and more the potential difference between the electrodes will increase, and as the potential difference increases, there will be a induced the EMF will be measured here. Okay, so I will again explain this part. The electrolyte in the working electrode is separated from the sample solution by an ion selective membrane, which contains a carrier for the analyte ion, and the exchange of ions at the ISM, that is ion selective membrane solution interface, results in a potential difference that depends on the analyte concentration. So more the concentration, more the EMF. The potential drop, which depends on the analyte ion concentration, will be the potential difference at the ion selective membrane solution interface and the ion selective electrode. Okay, now the same thing what we have seen in this picture on the right side. Okay, this is a good old electrolysis technique. Now we have not followed exactly this electrolyte technique, rather this is a dry electrode technique. Okay, of course the same AgCl has been used as the ion selective electrode. Okay, and ion selective membrane is prepared again by the same methodology. Okay, but this is a dry one actually. Fine. So let us go through the points so that to understand this process in a better way. Use of miniaturized solid state ion selective electrodes that measure the potential within the membrane directly without using the use of a filling solution. So that there is no solution, analyte solution, as I said. A set of disposable solid state ion selective electrode, paper based strips containing working electrode with the nitrate selective ion selective membrane and reference electrode with AgCl layer. So you see this point you have to note, nitrate selective ion selective membrane. So it will select, or it will allow only the nitrate ions inside. The key sensing mechanism of the printed ion selective electrodes occurs at ion selective membrane sample interface of the working electrode via the phase boundary potential between the ISM and the aqueous sample. That is a phase boundary potential. That is, the potential difference will occur between the ion sensing electrode and the ion sensing ion selective electrode and ion selective membrane, and that potential difference will be measured. And this phase boundary potential at the membrane solution interface arises due to nitrate in solution selectively diffusing between the aqueous phase and the membrane. The sensor electrode acts as the transducer element to convert ionic concentration into an electric potential. The electric potential is then processed for amplification to make it readable with a controller. The analog signal is then plotted. So this explains the entire procedure for the development of the ion selective electrode and ion selective membrane, and also how it processes the nitrate nutrient and able to sense it in terms of the potential difference. Fine. So the left part is the conventional method and the right part is the one what has been developed. And you'll be able to see the size of these electrodes. This way a 1 rupee coin has been placed next to it to show the, of course, it is not in the order of micrometers, but definitely it is in the order of a few millimeters. Okay, so that is why I said it is not exactly MEMS, because MEMS means it all has to deal with at micron level. Okay, yes, one maybe in future think about a MEMS related application in this kind of thing, but anyway ours is not that. Fine. Now these electrodes, see, one is made of carbon, that is ion selective membrane related electrode, and the other one is made of silver, that is ion selective electrode itself, that is the reference electrode. So reference electrode is made of silver, and the actual sample that is going into this electrode, that is made of carbon. Okay, because carbon has got some better properties. Okay, and now this is the actual sample of the electrodes what has been developed, that has been shown here. Then formation of conductive transducer layer. Okay, the electrodes are screen printed on either PET sheet or photo sheet as the substrate. So that is the substrate. By literature, high specific area carbonaceous materials have shown to offer high electric double layer capacitance and super hydrophobicity. The second point is nothing but the material which has got the super hydrophobicity, okay, is the one which does not allow water molecules, okay, to be on its surface. Means if you pour any water molecule on the surface of this material, it will simply run away. It will not stay there. Okay, so it is a water resistant quality of that material. Okay, then the carbon ink is first screen printed to form the bottom conductive layer for the electrodes, serving the dual purpose of the electrical contact and ion to electron transducer due to their chemical inertness, hydrophobicity, high surface area, and surface electron mobility. It results in a highly sensitive electronic response to the potential difference generated by the membrane ions in the electric double layer and the membrane transducer interface. Okay. So now coming to the testing of the reference electrode. The fabricated reference electrode is tested with the standard commercial reference electrode. Both electrodes are inserted into a salt solution with the fabricated reference electrode as the working electrode and standard reference electrode as the reference electrode. The setup is connected to a potentiostat to conduct open circuit potentiometry so that the transient and steady state performance and potential difference could be analyzed. Ideally, if both electrodes are functioning properly, there should be a little, that is less than 20 millivolts or no potential difference. Which means here what has been tested, we have developed a reference electrode, and that reference electrode has been tested against a commercial reference electrode. The commercial reference electrode has been already calibrated. So commercial reference electrode is calibrated for 0 volts, and we are now testing our own developed reference electrode against the commercial reference electrode, and it is found that the potential difference is less than 20 millivolts. So that shows that our reference electrode is of a very less voltage, which is very close to 0 volts. Okay, so it should be able to now act as a reference electrode. Now, large potential difference indicates that the reference electrode may be a faulty one. Okay, now calibration and testing has been done, as I said, of the reference electrode against the calibrated commercial electrode. So this is, test setup shows that our own developed reference electrode has been tested against a calibrated commercial reference electrode. Now the potential difference between them is less than 20 millivolts. Okay, and here this shows the corresponding values. Of course, I'm sure I know that the values on the left hand on the y-axis, it is not pretty clear for you, but I'm sure that these volts are the voltage difference between these two electrodes is very small. Okay, as the concentration increases from 0.01 mole for KCl solution to 0.1 mole to 1 mole, okay, slightly the potential difference increases. As the concentration increases, the potential difference also increases. Of course, I am not given you the exact values. Okay, now fabrication of a working electrode. So working electrode is the most crucial one, as we know. So that has to be fabricated, and finally the testing can be taken place can be done for the soil nutrient. So the carbon plate was already screen printed during reference electrode fabrication and dried at 150 degrees Celsius for about 30 minutes until it dries. The ion selective membrane is prepared with the mixture of tetra ammonium nitrate. Okay, and this mixture is used for the preparation of the ion selective membrane. This membrane is drop casted in the carbon layer using screen printing in different geometries being realized in simulation in order to compare and analyze the sensitivity, accuracy, and steady-state performance of varying working electrode geometry. As in the case of reference electrode, the ion selective membrane is also accommodated within the carbon conductive layer to ensure that the ion selective membrane layer is always in contact with the conductive carbon layer beneath. The ion selective membrane layer is then allowed to dry. Okay, so these are all the screen printed reference electrode and ion selective membrane related electrode, that is the working electrode, okay, of different dimensions and of different designs. Okay, now potentiometric response of nutrient sensor. Okay, so we have now prepared the reference electrode and the electrode which houses the ion selective membrane. Okay, and now the final testing has been done with these two electrodes with respect to the nutrient, that is the nitrate nutrient. Okay, so the potentiometric response of the nutrient sensor, will see the PBP, that is the potential difference that is building up between the reference electrode and the ion selective membrane. The PBP at the membrane solution interface arises due to nitrate in solution selectively diffusing between the aqueous phase and the membrane doped with the ion selective carrier, while the resulting potential difference yields nanoscale electric double layers on both sides of the membrane solution interface in situations where the potential difference is due solely to the selective transport of nitrate. The total potential difference can be evaluated by solving for electrochemical equilibrium between the two phases. This potential is described by the Nernst equation. So I'm going to tell you a few words about Nernst equation in the next slide. The working electrode is also tested with the potentiostat for verifying the concentration of nitrate salt solutions. So this is calibration and testing of nitrate sensor. The fabricated sensor results in a constant decreasing slope of 100 millivolt per decade for increasing concentration of nitrate ions. That is what is shown. So nitrate ions, as it is increasing, then yeah, it shows here decreasing slope of 100 millivolt per decade. Okay. Now, coming to the Nernst equation, this is the governing equation based on which the potential difference has been determined. Okay, I mean, I would say the potential difference is rather measured. Potential difference is rather measured. So let us look at this equation. E is equal to E naught minus 2.303 RT by NF log K, where E is the measured potential and E naught is the standard cell potential, R is the universal gas constant, T is absolute temperature, N is the number of electron, F is the Faraday constant, and K is the concentration. Actually, we, as I said earlier, we are interested in the concentration, that is K. Okay, the rest of the all other values R, T, N, F, okay, E naught, E, everything are either constants or measurable. Okay, in this case, E on the left hand side is a measurable value, and that is nothing but the potential difference between the reference electrode and the ion selective membrane electrode. So that potential difference we are able to measure. And E naught is a constant actually that depends upon the value, the initial value of voltage of the reference electrode. Now, this Nernst equation is applicable for a purely electrolysis process, but in the present case, what we have discussed, it is not purely an electrolysis process because it doesn't involve any analyte solution, because we have used only dry electrodes. So that means where we have applied the soil sample solution, we have applied the soil sample solution directly on top of the ion selective membrane itself, on top of the ion selective membrane itself. Now, once the ion selective membrane absorbs or attracts or allows those nitrate related ions inside the electrode, and the electrode gets more and more relatively higher potential with reference to the reference electrode, and you will be able to measure that value using the potentiostat, the instrument what is being used for the measurement of voltage. Okay, so that is how we measured the voltage E between the reference electrode and the ion selective membrane electrode. Okay, and at two different values of this concentration of nitrate, the potential has been measured, and we have got the values of E1 and E2, and if you subtract them, you will find that E naught is cancelled. So E naught, if you don't know, also no problem. Okay, what is E naught? E naught is the standard cell potential. If you don't know that, also no problem. Simply find the potential at two different points and subtract them, then E naught will vanish. Okay, from the rest of the things, you will be able to determine the value of K, that is concentration of the solution. In our case, it is the nitrate solution. Okay, so if you directly apply nitrate solution on top of the ion selective membrane, then the ions will be permitted inside the membrane, and that will reach the working electrode, and that electrode will now get higher potential, and that is being measured. Okay, that is how Nernst equation has come to our rescue to determine the concentration of nitrate solution. And finally speaking, this is nothing but the Internet of Things based crop suggestion system. So here you are seeing that this kind of system can be used for passing the information whatever has been sensed using our sensor. Okay, you can create a database over a period of time of different soils. Okay, not only that, you can, every time you do the testing part, you can provide the signal out to the farmer. Okay, so the testing can be done at a laboratory, where from the laboratory to the farmer the information will go, or the farmer himself will be able to given this kind of material, so that he can himself find the nutrient concentration. Okay, so the concentration of the nutrient, if it is high, then it will reflect with a higher potential. So if you calibrate for the concentration for the potential difference, then you will be able to create a kind of lookup table, higher concentration, then higher potential difference. The higher potential difference means reversely higher concentration will be shown to the farmer. So the farmer will be able to make his decision whether sodium is high, potassium is high, or nitrate is high. The farmer will be able to identify, and he will be able to make his own decisions for a particular crop which needs more nitrate or which needs more potassium of that sort. So this is what I wanted to say in this my brief presentation on the soil testing procedure. Okay. Of course, I will tell you this entire procedure as an electrolysis method. It is not new, okay, but some of the things what we have explored with the dry electrodes is something new, and we propose it to kind of implement and one day give it to the farmers, in the hands of farmers, so that they'll be able to test things on their own and take decisions on their own. So here ends my presentation. Okay, I will conclude now. So various methodologies are there to detect soil nutrients, which are already available in the labs. But as I said, they are a little bit cost involved, and there is also involvement of time that can be now lessened with respect to the farmers. So site-specific sensors required for precision agriculture farming are discussed in this presentation. The design for planar electrochemical sensor was also presented. So here I conclude, and I am open to questions or queries whatsoever. Thank you.
Thank you very much, sir. Presentation was very elaborate, and the MEM sensor application in soil testing was being explained very in detail. And now it's time for the queries. The participants can raise your questions.
Dear participants, please can raise your question. Sir is waiting.
Nice presentation, sir. I am Suman Saurabh.
Yeah.
Can you hear me, sir?
I'm able to
It's
hear
a nice
you. Yes,
presentation. Yeah. It's very informative. Sir, I want to know that electrolytic, whatever the things initially explained in for chemical by two electrode, that is feasible for doing farmers.
I'm sorry. Again, you repeat your question.
Sir, for electrolytic things, electrode, using electrode and doing electrolytics and generating voltage difference and ion generation. These are the things are feasible for the farmers, so they can use easily these types of devices.
No. That's what I told. Actually, what method has been developed is not exactly electrolysis, because we are not involving any analytic solution. That kind of thing we are not doing. We have developed dry electrodes, and directly the sample can be applied on the dry electrode on the membrane. Okay, and the membrane will absorb will allow the ions to pass through to the particular electrode and develop potential. So it is a dry electrode process. It is not involving any electrolyte.
Okay, sir. And so that cost is feasibility. Cost is feasible for buying all this for farmers, or is going very high, sir?
I think the cost will be very much within the reach of the farmers. It should not be costing very high. Very much.
Okay.
I mean, it will be just a few hundreds. Yes.
Okay, sir. Thank you, sir. Thank you.
Yeah, you are welcome.
Any questions from participants? Sir, I think
yeah.
there is no question.
yes. I think everybody has understood. So maybe if no more queries are there, we can conclude here.
Of course, your speech is very informative, sir.
Okay, thank you.
Because yes, soil nutrients and all. We have learned more from your speech. Thank you very much,
Okay.
sir.
Okay. Welcome. You are
Thank you.
welcome. Yeah.
Okay, sir. Suppose participants having any queries, then they will ask.
Yeah. You please let me know. Yeah.
Yeah, yes, sir. Yes, sir. Yes, sir.
I am ready to interact with them. Yes.
Yeah, yes, sir. Okay, sir.
Yeah.
Okay,
Okay.
sir.
Thank you for the opportunity. My presentation was, I think, was very brief in that sense, but I hope it would have been useful for all of you. Thank you.
Thank
Thank
you,
you,
sir.
sir. Thank you so much, sir.
Yeah. Thank you. Yeah. I'm closing. Then I will close the
Yeah.
presentation.
Ah, yes, sir.
Yes. So if it is done, then shall I leave the meeting?
Yeah, sir. You can leave it, sir. Thank you so much, sir. Okay, sir. Okay. Okay.
I
Thank you,
am
sir.
leaving. Yeah. Thank you. Thank you. Thank you.
Dear participants, we have sent all of your feedback and what the attendance and all. We will send you to your registered email ID. So please, all of you fill it and send it immediately. Okay, because this speaker is already early. He wind up now. So due to this, already we have programmed to reach you by 3:20 or 3:25 like that. The feedback form and attendance and all. But due to this time management and everything, it's so you can find in your mail ID, then you can fill it. No issues.
Okay, ma'am.
Okay, okay.
Okay, ma'am. Thank you.
Thank you. Yes, thank you. Our participants, if you want to ask any question or like that, if you have any doubt regarding this attendance, feedback, and so many things. Okay, fine. So, shall we wind up with this? For next 2 days, so please be on time because a few members they have joined by for 9:30 session. Few members they have joined by 10 o'clock or 10:30 like that. So feedback and all we have not received properly till now. So please, you all cooperate with us. Thank you. Yes, sir. Ifran Khan. Yes, sir. You want to ask something? Ifran, Ifran Khan, sir. I think you raised your hand. Okay.
Ma'am, shall we leave the meeting?
Yeah, you can leave it now. Tomorrow
Okay.
again.
Okay, ma'am. Thank you.
Such a wonderful session and informative session. Thank you, ma'am.
Thank you. Thank you.
Thank you, ma'am.